According to the second postulate of Dalton theory, atoms with the same number of protons are going to be chemically identical. However, they could have different masses because of different number of neutrons. That will lead to different isotopes of the same element. Hydrogen, you can see that in all three cases it has one proton, which determines the chemical nature of the atom to be hydrogen. However, the different number of neutrons will lead to different masses of each one of these, or what we call different isotopes. Any sample of any element will naturally contain at least two different isotopes. For example, a natural sample of uranium will contain uranium-238 and uranium-235, and any naturally occurring sample of uranium will have different fractions of each one of these isotopes. First thing we want to discuss about the different isotopes is their stability. Any nuclide or with an atomic number of 83 or more is going to be unstable, which means the nucleus will be vulnerable to nuclear decomposition to smaller atomic numbers. Lighter nuclides will be stable when the number of protons equals the number of neutrons. The ratio between number of protons and neutrons is 1. And for heavier elements, in order for the nuclides to be stable, that ratio will tend to go higher than 1, up to like 1.5. Sometimes certain combinations of protons and neutrons have special stability, so even numbers are going to be more stable than odd numbers, and some other special numbers have special stability. And these are called magic numbers. It's a plot of the number of protons versus the number of neutrons in a stability chart like this, and it's used in a similar way to the periodic table to explain patterns of nuclear stability. So all the red dots here are the stable nuclides, and all the blue dots represent other isotopes that are not stable. Stable nuclides occur in this stability region right here that is called the belt of stability, and you can see that that belt corresponds to a ratio of 1:1 between neutrons and protons for light atoms, and as you go to heavier atoms the ratio shifts from 1 to higher numbers up to 1.5 for the highest stable atoms right here, and anything above an atomic number of 82 is going to be unstable. Different isotopes will have different nuclear stability, and that is the basis for nuclear reactions. The uranium isotope that undergoes nuclear fission reactions is the uranium-235 isotope. The fraction of uranium-235 isotopes in any naturally occurring sample of uranium is less than 1%. And this is not enough for a nuclear reaction to take place, because the existence of uranium-238 isotope around kind of switches off the fission reaction. So we have to increase the fraction of uranium-235 isotope in the sample. This process is called enrichment. So if you achieve something between 3 and 4%, this is going to be enough for a power generating fission reaction in reactors. But in order to make nuclear weapons, you have to achieve above 90% enrichment of uranium-235 isotope, which is a significantly technologically challenging task. The masses of different isotopes and their abundances or fractions in the sample are determined experimentally using a technique called mass spectrometry. The instrument used for that, the mass spectrometer, has a design similar to this scheme right here, where you vaporize your sample and inject it as a vapor into the instrument. Then when the sample vapor gets into the ionizer, it turns from neutral atoms or particles to ions. This is the first step, which is the ionization step. And then that flow of ions gets accelerated using accelerating plates. And then the beam of accelerated ions passes through a magnet. An electrically charged particle passes in a magnetic field, get attracted to the magnet one way or the other. So we modulate the magnetic field to a certain level to cause a curvature in the path of the flow. So that curvature will depend on the mass of the charged particle and the magnetic field of the magnet. So we modulate the magnetic field, so anything that is heavier will not curve enough to pass through, and anything that is lighter will curve too much and will get discarded, and only ions of certain mass will go through the tube to the detector. That way you can accurately measure the mass of each ion that passes at each time. So you scan the magnetic field to get the different masses of the ionized particles in your sample, and or the number of particles that passes and hits the detector will show up as intensity in your detected signal. So a mass spectrum like this will give you the different masses of different isotopes existing in your sample with a resolution as high as 1 proton difference between isotopes, and the intensity will give you the relative abundance or the fraction of each one of them in your sample. So the percent abundance or the relative abundance of each isotope is found as a ratio of the number of atoms of that isotope to the total number of atoms in your sample times 100. It usually is expressed as a percent out of 100, but sometimes you can find it expressed as a fraction abundance. The atomic weights that we see in the periodic table are actually weighted averages of all the individual isotopes. So you take the percent abundance of isotope 1, divide by 100 to convert it to a fraction, and then multiply it times the mass of isotope 1. That's plus percent abundance of isotope 2 divided by 100 times the mass of isotope 2, and so on. Carbon has 2 isotopes, carbon 13 and carbon 12. Carbon 12 has the mass of 12 AMU, and carbon 13 has the mass of 13.0034 AMU. The relative abundance of carbon 12 is 98.89%, and the relative abundance of carbon 13 is 1.11%. To calculate the atomic weight of carbon, this is gonna equal the percent abundance of carbon 12 divided by 100 times the mass of carbon 12 plus the percent abundance of carbon 13 divided by 100 times the mass of carbon 13. Percent abundance of carbon 12 is 98.89%. Divide this by 100 to convert it to a fraction. Multiply it times the mass of carbon 12, which is 12 AMU, plus percent abundance of carbon 13 is 1.11%. Divided by 100. Multiply it times the mass of carbon 13, which is 13.0034 AMU, 11.87 AMU plus 0.144 AMU, which will have an average of 12.01 AMU. This here is the average atomic weight in a sample of naturally occurring carbon. So we know that the atomic weight equals the percent abundance of isotope 1 times the mass of isotope 1 plus the percent abundance of isotope 2 times the mass of isotope 2. In the previous example, we were given the relative abundances and the different masses of different isotopes, and we were able to calculate the atomic weight. We can go the other way around. If we know the average atomic weight of a sample and the masses of the isotopes, we should be able to calculate the relative abundances. So in this example right here, we have copper, which has an atomic weight of 63.55 AMU, and this number here should be the contribution from isotope 63 and isotope 65. So it should equal mass of isotope 63 times the abundance of isotope 63, expressed in fraction form, plus the mass of isotope 65, which is 64.9278 AMU, times the abundance of isotope 65, expressed in the fraction form. So if we put this in an equation, the atomic weight should equal mass of isotope 63 times the abundance of isotope 63 plus mass of isotope 65 times the abundance of isotope 65. We know this, we know this, we know this, but we don't know these two. And it's not possible to solve an equation for two variables. So we need to simplify this equation somehow. We're gonna use the fact that the abundance of isotope 63 plus the abundance of isotope 65 has to equal 100%, since those are the only two isotopes in the sample. Or if you express it in the fraction form, it's going to have to equal 1. So if we put isotope 65 as x, so isotope 63 abundance plus x is going to equal 1. If you subtract x from both sides of the equation, that will give you that the abundance of isotope 63 equals 1 minus x. So the atomic weight is gonna equal mass of isotope 63 times the abundance of isotope 63, which is 1 minus x, plus mass of isotope 65 times the abundance of isotope 65, which is x. We know this, this, and this, and now we have an equation in one variable, which is x. So we will rearrange to solve for x. So this is going to equal mass of isotope 63 times 1 minus mass isotope 63 times x plus mass of isotope 65 times x. So if we subtract the mass of isotope 63 from both sides of the equation, the atomic weight minus mass of isotope 63 is going to equal mass isotope 65 times x minus mass of isotope 63 times x, or x times mass of isotope 65 minus mass of isotope 63. So if we divide both sides of the equation by this term right here, this will cancel with this, and it's gonna equal atomic weight minus mass isotope 63 divided by mass of isotope 65 minus mass of isotope 63. So we can solve for x. Atomic weight is 63.55 AMU minus the mass of isotope 63, which is 62.93 AMU, divided by mass of isotope 65, which is 64.9278 AMU, minus the mass of isotope 63, which is again 62.93 AMU. So x is gonna equal 0.62 AMU divided by 64.9278 minus 62.93, which is 1.9978 AMU, 0.3103 as a fraction. Or if you want to express it in percent form, you multiply times 100, and it's going to equal 31.03%. This here, based on our initial assumption, is the abundance of the 65 copper isotope. We can calculate the abundance of the 63 isotope to equal 1 minus x, or 1 minus 0.310, and it's going to equal 0.689658 fraction, or again, if you want to express it in the percent form, it's going to be 68.97%.